Hi everyone, this is Sir Fredrick Mlenga. Today I want to attempt to drive the 4 kinematics equations. Those equations which our teachers by then used just to give us to calculate, because by then we are just doing physical sciences. So indeed it was unnecessary to drive those equations. But for those who are doing real physics, those who are physicists, maybe those who are doing A levels, it is very much important to appreciate where these equations come from. So today I'm going to attempt to drive them so that we could appreciate the knowledge of physics. And this also helps you to know when you are designing something. You're designing an aeroplane, when acceleration is constant. Indeed, you need to know where the logical conclusion of these equations are coming from. So hence today I'm going to try to do that. So let's do some really real physics. All right. So we know that the definition of acceleration is that it's a rate change of velocity with time. And this in physics is represented by this core formula: acceleration is equal to dv dt. Okay, so you differentiate some infinitesimally velocities, or the change in velocities, and over time. Okay, so if we have this and we want to make v as a subject to the formula, so we are going to do this cross multiplication right there. Okay, so 1 times that is going to give us dv is equal to a acceleration dt, something like that. All right, so when you reach this stage you integrate. Okay, so you put an integral sign there. Okay, you integrate both sides just like that. Okay, so this means that the summation of infinitesimally change in velocities, when you get all those things, you add up all the small change of velocity, you're going to get just all of it. Okay, so all the other reasoning you can give here is that differentiation is opposite to integration. So this sign goes with this d, then we're gonna remain with what? You're going to remain with the velocity there. Velocity is equal to, then again here what we have is that we have acceleration, which is a constant. So acceleration, which is a constant, gonna go out. Okay, and you are going to remain with what? You're going to remain the integral of dt, and this will be also the summation of some small change of time. It will still give us what? The total time there. So this goes with that. So we're going to have what? We're going to have a t there. All right, so now the rules of integral calculus is that after you integrate, you add a constant. So this constant in calculus, you just put c there. Now what is the meaning of this constant in physics? Or since in mathematics you just integrate and you put a constant here, so the constant in the physical world means the initial conditions, when everything is at initial condition. So for us to say this vehicle is moving, definitely we should have a reference when it was not moving, when it was at rest, when the time was 0. So initial condition simply means that the time is 0 and maybe this object is at rest. Okay, so we are going to have what? We are going to have when something is at rest, so the velocity gonna be velocity naught. Okay, so now let's try to replace these initial conditions in our equations. So when 8 is equal to time is 0, okay, then our velocity gonna be velocity naught or v naught. So let's now reverse this. So I'm going to write where there is, we are going to replace this velocity naught where there is v is equal to at. Okay, so where there is t, we are going to assume we are at 0, so the initial will be 0 there, then plus c. So v naught is equal to a times 0 is going to have 0, then to give us what? C. So what does this mean? That constant we put after integration in mathematics in science means the initial velocity, and in this question, I mean in this context, our constant is initial velocity. So we are going to rewrite this equation where there is, since we are telling us where there is v naught, where there is c, we'll put v naught. So I'll get the same equation now. So v is equal to at plus, I'll put now that, so v naught. Okay, so if I rewrite this properly, it's going to be v is equal to v naught plus at. So this is the first equation, hence shown. Okay, so we've derived the first equation just like that. So let's derive the second equation. So say equation 2. Okay, so equation 2 comes from the definition of velocity. Velocity is defined as the change in displacement with time, and physicists define velocity as v is equal to dx of dt, just like that. So if we play with mathematics here, cross multiplication, want to make x as a subject of the formula, so it will be dx is equal to v dt. Okay, so when you reach at this point, you will remember that you've derived the first equation. So, and in fact, all the equations comes from these first two equations. So the first equation, we said it is velocity is equal to v naught plus at. So where there is v, velocity, we are going to replace it with that expression. So this will come here. So so what we're gonna do is, so dx is equal to v naught plus at dt. Okay, so once you do that, then you integrate this expression. So we are going to introduce the integral sign on each of the expression. So integral of dx gonna be there v naught dt plus integral of at dt. All right, so what do we do now? So the summation of the infinitesimally change of displacement is going to give us just what? The total displacement there. So this means that this and that goes, so x is equal to, all right, then v naught is a constant, so it's gonna come out, okay, like that. Then if we integrate this and that, or the summation of infinitesimal small time, it's gonna give us just the total time. Or the other reasoning you can give is that when integrating, you are going opposite as differentiation. So the integral sign and that differentiating, it goes. So we're gonna have what? T there. All right, then plus acceleration is constant, so it's gonna come out of the integral sign, so it's gonna be like that. Now here, let me take some little bit about the law of integration. Okay, so since this has come out, so we've remained with this integral of this dt. So when you have this, you are integrating this, the rule or the formula of integral sign is going to be t the power plus 1 over the power then plus 1. So since t is raised to the power 1, so it's going to be t power 1 plus 1 over 1 plus 2. So this is going to give us t squared over 2. Okay, so we're going to pick this and replace it in our formula. So we'll take it just right there. So t squared, oops, let me try to change the car. Okay, t squared over 2. All right, so v naught plus, so the exponential of this all things is half of this, then at squared. Then I think you've seen this equation before. Okay, so this is where it came from, this equation. All right, so now after you integrate in mathematics, you always put a constant, and we know what it means, constant in physics. So the constant means the initial condition. So we'll apply the initial conditions here. Initial conditions. So we know that at when time is 0, our displacement will be what? V is equal to V naught. So we'll express our equation in form of initial conditions. So x naught is equal to V when a time is 0, so we'll put 0 there, plus half of that acceleration, then our time is 0 squared. So all these things will give us what? I mean plus c. So all these things multiply by 0, it's gonna give us that. So x naught gonna be c. So where there is c, we'll put what is telling us that is that. So if we now rewrite the equation, we'll rewrite it, so it will be x is equal to v naught time plus half at squared. Where there is c, we put what? We'll put x naught. All right, so the rule of mathematics is that when this crosses the equal sign, it's gonna be x minus that is equal to v time plus that acceleration squared. I hope you've seen this equation before. Okay, so that's where the equation come from. So this is equation 2. All right, this same equation can be also expressed, if you want, you can express it in this way. Where there is v naught, you just use u. So x minus this is equal to, where there is v naught, I'll put u. That this is the common equation that you could see in most books. All right, so having derived these two equations, all the other equations come from these two principal equations. Okay, so what we could do, just start from this equation and derive the other ones. Okay, so let me try to attempt the equation number 3. So as I told you, the other equation come from these two, so I'll write them here. So v is equal to v naught plus at. Okay, the other one which we've derived also is x minus x naught is equal to v naught t plus half at squared. All right, so we'll begin with this equation. Let's deal away with this equation. All right, so what we are going to do, we are going to make acceleration as a subject of the formula. So v is equal to v naught plus at. So I want to make this as a subject of the formula. So this will come this side, so it's gonna be v minus v naught is equal to at. So I want to remain with acceleration, so I'll divide both side by t, so that goes with that. So acceleration gonna be v minus v naught over time. All right, so now we'll come with now this equation, now the second equation. Now, so where there is acceleration, we'll replace with this expression. So we'll start. All right, so x v naught minus v naught that plus, so where there is acceleration, I'll put this, of course, v minus v over t. Okay, over t. Okay, then that gonna be t squared. All right, so perhaps you can do away with these since you have time squared here. This time squared goes with that. So if we rewrite this properly, we are going to have that v naught times time plus half, okay, v minus v naught and time. Okay, and time. So now here this half is multiplying everything inside the brackets, including time as well, is also multiplying everything inside the brackets. So if we were to do this, this means that we're going to write it in this way. V naught x naught is equal to v naught time plus half times v. Okay, it is v, and t times v as well, it will be vt. Okay, just like that. Then you go there, half times v naught, it's gonna be half v naught and t, just like that. So when you reach this stage, you actually check out the like terms, so you group them like terms together. Okay, just simple math here, which we used to do. So like terms. So if you have noticed, you find out that this and these can be grouped. So the coefficient here is actually 1. So if you group this, you're gonna have that. So let's try to do on the sides just a little mathematics. Okay, so v naught with a coefficient of 1, then I'll lift the entire this there. Okay, I'll lift the entire that there. So minus half v naught. Okay, let me try to leave this one. Okay, so if we do the mathematics just right up here, okay, that times that, it's going to be 2v naught t, okay, minus 1 times that, it's gonna be v naught t, just like that. Then this will be over 2. Okay, this will be over 2. So this can go with that. What are you remaining with? If you subtract this from there, you still have, okay, oops, let me not do that now. So that times that, 2v0 minus v0 is going to give you v0 over 2. Okay, so you lift up this, you take it now in the equation. So if you rewrite it, it's going to be vx naught. Okay, so it is no longer there. So what we are going to have, now, we are going to have 1 over 2 v0, okay, then plus 1 over this. We'll just depress this back there where it belongs, so vt. All right, so what are we going to do here now? So we'll factorize now. So that is equal to, so since half is common in this one, it's gonna come out half. What else is common? Time as well is common. So what is remaining? We're gonna have v naught plus v, then just like that. So now you rewrite this equation as this is equal to just like that. Okay, so this is the third equation. This is where it comes from. So some books, they present this as that. Okay, it is written as where is u, you put u, then v, like that. To drive the fourth equation, we are going to begin from what we know from these two principal equations. So we are going to solve for t. We are going to make t as a subject to the formula. So this is gonna be v minus v naught is equal to at. So if I want to remain with t, I will divide both sides by a, then t gonna be v minus v naught over a. All right, so we are going to place all this expression in this second equation where there is t. So let's try now. Let's do with this. Okay, so x minus x naught is equal to v naught. So we're gonna plunge in that over a, half a. So then v minus v naught over a squared. So you know, this is a pain that we are going to go through because we are going to square all of these things. So make sure you understand what I'm going to do right now. Okay, so so we are going to distribute v naught across this. So and this is going to give us x minus x naught. So that times that gonna v, that v naught times v naught squared over a, then plus so then we are going to have half that. So now we are going to square these a lot of things. So let me solve it just meanwhile somewhere so that we get to understand what is happening. So v minus that over a, then v naught over a. Okay, so we are going to multiply that times that is going to give v squared Okay, then that times that v naught. Okay, so we begin with this, that times that, we are going to have v naught, then that times that positive, so we are going to have v naught squared over a squared. Okay, so if we want to deal away with this, so v squared, this plus that. Okay, so keep this, and we're gonna have 2v square v naught plus this squared over this. Okay, so once we have this, then we can get this and take it in the entire expression. So this is how it came up. So I was avoiding to go direct because I couldn't know where it came from. Okay, so so I'm gonna take this expression, and since I'm distributing across, so it's going to be v squared 2v naught plus v naught squared over a squared. So since we are having two a's, so this will cancel with that one, so we are going to remain with that. So I'm going to break this into components so that it is easy for us to deal with it. So start as usual. Okay, so this is equal to v naught v over a, then v naught squared over a. Okay, plus half. So this half going to be distributed across, so I'll start literally one by one. So this gonna be v squared over a, then these 2 times this half times that, it's going to go. Okay, so we are going to have v naught over a plus, then if this multiply that, it's going to be half v over a. So when we've reached this point, we have to check to group the like terms together. So if you check this and this minus, so they cancel each other, that goes. Let me check if there's also other things that are canceling each other. Okay, so if you've noticed here, we have 1, -1, that's as a coefficient. Here we have plus half. So if we do away with this, so -1 plus half. Okay, so that times that, -2 plus 1 over 2, so this is gonna be negative half. So this will get this coefficient, meaning it has dealt away with this and that. So it will be x minus x naught is equal to so minus half of this. Okay, then plus this, so half VA. All right, so now when we are here, we don't want to have this fraction, so what we are going to do, we are going to multiply by the denominator. So both sides will do with 2a. So let me try to adjust this so that it can move a little bit here. Okay, both sides is 2a. So this goes with that and goes with that. So 2a x minus x naught is equal to negative 1 times v, so we'll keep that, negative v naught squared plus v squared. Okay, so when we reach here, we can just do manipulation with something here. So if this crosses the equal sign, comes this side, so we're gonna have 2a plus v naught squared is equal to v squared. So when we write this properly, it's going to be v squared is equal to v naught plus 2a that minus x naught. Okay, so hence we've shown here. Okay, this can be also, some books they present this equation as v squared, where there is v naught they will replace with u, initial velocity, plus 2a x, just like that. This is same thing. So this is where this equation come from.